In the previous video, we looked at the definition of a directional derivative. In this case, if we're looking at a function that depends on x and y, and we have a given unit vector with components a and b, this is how we calculate it. It's the same as a derivative from first principles, very similar to partial derivatives. But the big difference is now we're varying, in general, x and y, and if it depends on z, we would also be varying it with component c. What we now want to do is to find an expression that is much simpler, that we can apply without excitation to calculate directional derivatives. So let's get onto it. And you'll find this in your lecture notes in section 10.4. To do this, and I'll try to go step by step, following the lecture notes so you can refer to it. Some steps may not be completely obvious, but if you pause the video, go back, or if you have your lecture notes side by side with the video, I hope it makes it clear. If there's any step that you don't get, please just get in touch, and I'm more than happy to explain. First of all, first step is we'll define a new function that only has one variable, which we can write as g of z equals to f x0 plus a z, y0 plus b z. And as pointed out in the lecture notes, this is just a function of one variable because z is the only variable. The other things are constants. Let's say that we want to differentiate this function. Because it only depends on one variable, this is relatively straightforward. And from first principles, you'd write that this is the limit when h goes to 0 of g of z plus h minus g of z over h. It's relatively straightforward. Now let's say that we also want to calculate this derivative when z equals 0. When this happens, all we do is we're calculating g of 0. This is the limit when h goes to 0, and we're now subbing in. This is g of h minus g of 0 over h. Again, still very simple. Now, according to the definition, it's the first equation that we wrote, this one, and also in your lecture notes. We can understand that g of h, this is when we plug in h, it's the same as if you were plugging z. This is the same as writing f of x0 plus ah, y0 plus bh. It's just following the definition of gz. And in a similar way, we also know that if we plug in 0, we get f of x0. That's it, right? Because this becomes 0 and y0. And this implies that g of 0 is just f of x0, y0. Why is this useful? Well, it is useful because we can also write this. All we did is we've now expanded what these terms are. This is the same as saying the limit when h goes to 0 of g of h, that's f of x0 plus a h, y0 plus bh. This is all we did was we plugged this into here, and now we're going to plug this into this term. It becomes minus f of x0, y0, and divided by h. And if you paid any attention, you've watched the previous video, or you looked at the previous section, you will see that this is actually exactly the definition along a direction given by the unit vector u of f xy. Now we're not done yet, but this is important. What we've actually done is to establish that the derivative of this function g at point 0 is equal to the directional derivative of f xy. This is what we've achieved so far. It's not great, not that useful, but it will become useful in just a moment. Before it becomes really useful, we'll need to clear a little bit of the board. And remember, you can always go back in the video And also I am following line by line the lecture notes to make sure that you don't get lost in this derivation. What we can also write here is that g of z can be written as f of xy, provided that in this case that x equals x0 plus az and y0 plus bz. This is exactly the same as here. Again, it is still a function of one variable, which allowed us to use differentiation from first principle in a simple way, but also already allowed us to derive this. All we did really is to define this as a parametric function. Now let's say that we want to calculate, again, the derivative of g, and this will be really crucial, so we can link back to derivative from first principle and we can connect with the directional derivative. In this case, this would be the same as dg dz, and because g of z is equal to f of xy, where x and y are defined in this way, in terms of a parameter z, we can also write that this is the same as calculating df dx, and then dx dz plus df dy dy dx. It's chain rule and parametric differentiation. If you do this, you can very easily calculate these with parametric differentiation, or just realizing that x is a function of z, the derivative is simply a, dy dx, y is a function of z, the derivative is simply b. And the other thing that you can recognize if you've done section 8 is that this is the same as f of x. This is the partial derivative of f in respect to x. And this is the partial derivative of f in respect to y. This is fy. And the way we wrote this is f of x, y, and therefore this is fx of xy. And same thing here. We can therefore write it as fx xy times a plus fy xy times b. And the further thing we can do to simplify this is we can have a look when z equals 0. When it does equal 0, x just becomes x0, y becomes y0. And following this at z equals 0, the derivative of g equals fx at x0, y0 times a plus fy x0, y0 times b. And this is really crucial, useful, and a reason to cheer, because we've just seen that the derivative of g at 0 is the directional derivative, that complicated limit, but this complicated limit is just about calculating the partial derivative at a specific point plus the partial derivative at the other point and multiplying by the component of the unit vector. Allowing this x0, y0 to be any point, because they can be, we can very simply write that the easiest and the way you're going to be calculating directional derivatives along a given unit vector of a function that depends on x and y is simply by calculating the partial derivative at a point xy times the component in x of the unit vector plus fy xy times the component of the unit vector in y. This is what we were aiming for. This is what we've been able to derive. And I hope the demonstration is relatively clear. I did follow the lecture notes line by line so that you can very easily compare. And I hope that all the ingredients are clear. If that is not the case, if you have a question about a step, just please get in touch and I'm more than happy to help or to also cover it in the discussion session. The reason why this is so useful is because you already know how to calculate partial derivatives, and calculating unit vectors is also relatively trivial, which means you really have all the ingredients to calculate directional derivatives, to have a look at how functions, surfaces, or things of higher dimensions are varying along specific directions. There's of course nothing special about functions that depend on two variables. Let's get some space here. For example, if you're looking at a function that depends on three variables, then the way you write and calculate the directional derivative along a unit vector u, in this case unit vector u would have components a, b, and c. This directional derivative of f, x, y, z is just given by fx times a plus fy times b plus fz times c. Where in this case, when I write fx, typically mean fx of x, y, z. In this case, fy of x, y, z. And in this case, fz of x, y, z. In many cases, you want to keep the directional derivative general. In other cases, you actually want to calculate it for a specific point. So let's try to use these expressions to show you how easy it is to actually calculate directional derivatives.